All right, when we get started on unit 12 here, looks like we have Grace and Johnny online today, so nice to see you there. Okay. Um, Last unit we started talking about Turing machines and proving things with Turing machines, and looking through those, and we went through a lot of stuff. This unit we're going to revisit some of that stuff, especially the more complex stuff, and do a little more formal analysis of it. Last week we kind of looked at how it worked, but not so formally. This unit really is going to look at more kind of the mathematical or the underlying proofs on this. We're going to talk about proofs some, and then look at some of the proofs and kind of think of this more in that model here. Um, and so we're going to talk a little bit about just how we do mathematical proofs, because some of you may not, if you're not in a math class or haven't taken a math class in the last year, sometimes you kind of forget how these proofs work and what they are, and show. So we're going to just review what proofs are, how we structure them, and then apply different types of proofs to a number of these problems. So this unit probably is the most theoretical unit in the whole area. And again, the main reason for this is really if you're going into grad school or computational theory or something like this, where you're going to be wanting to understand and look at proofs a lot. You'd want to kind of understand this stuff. So this is what we're kind of looking at here. It doesn't have a lot of practical, meaning it's not going to help you necessarily be a better Python programmer, but helps you understand the theory behind this area. Um, so we're going to get started. Under the readings for this unit, I have the same readings as last week, these same two chapters from these same two textbooks. One is Introduction to Turing Machines, and the other one is on the Church-Turing thesis here. And then we're going to look at some prompts. I've run this through Gemini, so I'm going to walk through some of these prompts today and some other responses, and suggest you might want to run them through AI at the same time. So again, for your QQSP, we have this prompt, these prompts here, and we're going to kind of work through those. So kind of a typical Tuesday here, working through these prompts and seeing what they'll tell us for this. On Thursday, we're going to do an exercise that talks more about the limits of computation, and we'll let you work in small groups to kind of discuss more of the philosophical implications of this. What does this mean? What are the limits of computation? What can a computer do and stuff like that? So not so much related to proofs, but more in the theory of stuff. And this gets into what we call Church's thesis here, which is kind of the second part of it. We won't be covering that. We covered it a little bit last week. That just says that anything interesting that you can do in a computer, you can do in a Turing machine, basically. And anything that a Turing machine can't do, any other computer can't do, kind of that sort of idea. So Thursday, again, we'll get a little philosophical and talk about, or have you in small groups look at some of the limits of computing. And then the assignment this week is going to be doing some proofs. I'm really interested to see AI has some issues with proofs, but there's some new versions of the models out there that are better at proofs. So what I'll have you do, and I haven't quite finalized this, I'll have this hopefully done tomorrow so we can do it on, or you can start it on Thursday, is look at different AI systems and compare how they handle proofs and find mistakes in some and others. And so we'll give you some proofs. We'll have you look at it through a couple different AIs. And we'll talk about that even just today when we're doing this, what kind of AI systems you want there. So we'll do that as the assignment. Um, in order to get you there, we've got to get you to understand enough about proofs so you can recognize the errors that AI might generate in proofs. So we're going to jump into the prompts this week. And again, we've talked about, you can use OpenAI or Gemini and stuff like that, but we really haven't talked too much about, we've talked a little bit about the different models, and we'll look at that a little bit more today here. So, for example, in Gemini here, Gemini has a new version, Gemini 2.5 Pro, and it is, I think it's just in test mode. I know I can access it for free. It looks like currently, and it's again very good at this thinking. It's one of these kind of thinking model, a reasoning model. It's good at apparently coding, although I wasn't using it really well, except for coding Turing machines. So I was using that. It is again one of these what I'd call slow generative AI or reasoning models where it thinks for quite a bit before it answers. So you can see it does a number of prompts or actions, thinks about things, generates some stuff, and then answers the response. And the same thing is true with ChatGPT here. If I look at the different models, like 4.0 are just what we call kind of generative AI, generate the stuff, where like O3 a mini high is again, or mini is an advanced reasoning model here. So it's O1. You can try these out. I'm not sure what you can try out as far as the, I have a paid account, so I'm not quite sure which of these you can access. And they just released their 4.5 one. And again, I haven't tried that one out yet either. So we might. So again, for the assignment, we'll have you look at that. And similarly, what do we look at here? Deep Seek is the Chinese model here. Switch this over to English. And again, their model is a or you can click on a thinking model. So you can click on R1, a deep think, thinking version of this model, which will do more thoughtful responses. And currently this is free for everyone. So, okay, so let's look at some of this stuff. So let's just talk about the format of proofs. I have a prompt here just to say I prefer the 2-column version of proofs, but AI rarely writes it that way. So I often have to ask it to write it that way. Here, let's just look at Gemini stuff here. So this is how I like to see proofs. So, to me, in my mind, a proof is a step-by-step logical argument for something there. So we're trying to show something, and we're doing it step by step. And in each step, we should have a justification or a reason there. And so I like to list out the steps and then the justifications over here, kind of in a 2-column manner for this. So this is what I kind of like, is to show that, here are the steps here, and here's the justification for this stuff. So I kind of like that format, and I'll use that at times here. So that's what this is just asking for. Then let's look at the types of proofs. Again, if you're a math major or you've taken some math classes, you're probably familiar with these. But if not, you may not be that familiar with the different ways that proofs are done here. And so we can do that. We're just talking about where, language models. So like this is a type of question that's very straightforward, and that like in ChatGPT, just ChatGPT 4.0 would be very good at. It should, a quick response, just generate the response here should be fine because it's a very straightforward question. Doesn't require much thinking or anything like that. here. So let's just look at these responses. So we'll start with the simplest, what I call deductive proofs here. And in my mind, there's kind of two types of those. Proof by construction, where we just construct something, or proof by exhaustion, where we just try out all the possible cases. Here's a case, here's a case, here's a case, and show, that something. Usually, if we're showing something not true, we usually show all the different possibilities, and then we say, see, we've tried out every possibility, and none of them are true, or also try to show they're all true, something like that. And again, this is like straightforward logical reasoning, where you're going to try to show that this is logically true. You start with some premise or some thesis, theorem, and then you're building off of that. And your justification is usually some sort of logical reasoning or given facts that you have here. I always think like geometry proofs, and we'll see some proofs in a sec that are out there, but I always think of geometry proofs as a good example of these sort of deductive proofs. Proof by induction. This is when we want to show something is true for a lot of cases, like an infinite number of cases. And so this is, in my mind, is very related to recursion here in computing, in that we show a base case often where, the base case where, x equals or n equals 0 or something, the most simple case. And then we say, assume this is true for some general case and prove it for the next case. If we know it's good for one case, show it's good for the next case here. And we'll look at that. But again, kind of like recursion, or, at least tail recursion, where you have some base case where it gets down to this point, and then you do it. And then your recursive case, where you're given some value and then you simply break it down into, well, we can solve this by solving, or recursively calling it with one less, or with a less thing. And eventually that'll recur down to your base case. So in my mind, proof by induction is very much almost like proof by recursion, and is a computer way of thinking about it, I almost think. So proof by contradiction. Here, we just assume the opposite. We say, well, and again, sometimes people will almost call this the devil advocate way. We just say, oh, okay, if you think this is true, just assume it's not. And what happens? And we assume it's not, and we get to a contradiction, and we say, well, so this can't happen. So our assumption that's not must be false, so it must be true. The statement must be true because the contradiction was false here. So again, we just assume the opposite, derive a contradiction, and then we prove the original statement. In computing, we use this proof by a reduction a lot, and we'll see that today, where we'll have something proved, and often some complicated case. Like today, we'll show the halting problem here. And then we will show things are equivalent to the halting problem. And since the halting problem says, has a solution, then we can apply that solution to all these other problems here. Next week, when we get to like complexity theory and try to show how is an algorithm doable in exponential time or in linear time there, we will use the same sort of stuff there, where we can say that maybe this problem isn't doable and then in a reasonable amount of time there. And so if we have another problem, we can show that that's reducible or equivalent to this other problem, and then so it requires the same amount of time. So that's a little different, but again, the same sort of idea is this: we show equivalency between problems. And same here. Today we'll look at a number of things related to the halting problem and show that some problems are reducible to the halting problem. It also means that if you can solve any one of these problems, you could solve the halting problem here. And again, the fact that the halting problem can't is undecidable means that all these other problems are undecidable. The last one is kind of a specific example, is a proof by diagonalization here. And it's kind of related to proof by contradiction, but it's a special case of that. And that's where we will often assume the contradiction and then construct an element outside of this. And this is used a lot with infinite or sets and stuff like that. And we'll look at that. And again, we see this fairly often with Turing machines and computability, because we'll have infinite number of options or an infinite tape or things like that. So we can construct these long infinite values here. So let's kind of walk through some of these. But I'm just going to do some simple math stuff first and look at those as simple proofs to remind ourselves of proofs. So what have you done as far as proofs here? Have you guys done proofs? What kind of math have you done and stuff like that? Not really? Okay. Maybe in high school? Yeah. Yeah, same. Grace, Johnny, have you guys done much in the way of proofs? Let me bring up the chat so that's available to you if you want to type something in there. Okay. All right. So yeah, high school geometry, that's kind of the typical proof area. Okay, so let's look at some simple proofs here. And again, this is type of stuff where I think the basic AI is still working fine. So I can take this sort of problem and go in the normal chat GPT and ask it to construct one of these proofs here. So show that 12 is not a prime number here. So again, we're going to start with the definition of a prime number. A prime number is a number with two positive divisors, one and itself. That's the definition of prime numbers. And we're going to say that 12 has more than two divisors. It's a fact about the number 12. That's its reasoning. Okay, maybe ChatGPT 4.0 is not quite up to this sort of stuff. And for example, 12 is 3 times 4, construct the factorization of 12, and it walks through this. So again, that's the idea here is basically we want to by construction, we want to show that there are divisors of 12 and that it's not prime here. So again, here's the thing, similar thing. This is from Google Gemini. Prime number is whole number greater than 1. There's only two distinct positive divisors, one in itself here. So again, a little more detailed whole number greater than 1 with two distinct positive divisors here, one in itself here. So 12 is a whole, so we start going through the rules. It's a whole number greater than 1. So that's good. It satisfies this. But it then says 12 divided by 2 is 6. That's basic arithmetic here. And 6 is a whole number, obviously. So that means 2 is a positive divisor of 6. And 2 is not equal to 1 or 12 here. So and it's, again, referring to our previous steps here where we are doing this. So then now, since 12 has a positive divisor other than 1 in itself, it does not mean the definition of prime. And again, refers back to step 1, our definition of a prime. And therefore, 12 is not prime there. So I think that's a little better structure of a proof than what GPT 4.0 gave us here for this. Again, maybe a little longer. I think you could actually, do this in maybe 3 steps. Definition of prime, show that 12 has divisors, and then since it does, it's not prime, something like that. So now one other thing to remember is that with proofs, there are often multiple ways of proving something. So there isn't just one proof. It's kind of like programming. There's not one way to write a program to solve a problem. There's not one proof. There's not only one proof to do things. So we can prove this a number of different ways. In fact, just simple things. They took 12 divided by 2 and got 6. We could take 12, show that 12 divided by 3 is 4, and that would be fine too. So there are different versions of this. So again, they talk about that. So in fact, they say 12 is divisible by 2, 3, 4, and 6 there. And you could say it's divisible. It has lots of divisors here. You can also do some other ways. They talk about a proof by contradiction or other proofs. We are trying to do a proof by construction here, just construct the answer for this. And again, when we get to Turing machines, we'll see this sometimes where, the question is there a Turing machine that does this? And the answer will be, well, yes, here is a Turing machine that does this. And it show that it does it, prove that it does it in some ways. In the same way, sometimes, like, is there a program to do this? You can say, well, yeah, here's a program. It does it for this. So that's what we kind of see by proof by construction here. Proof by exhaustion, let's do that next. So that, again, a good example like that is prove that 7 is a prime number here. So again, we're going to define what a prime number is. It can only be divisible by 1 and the number itself here. So then our proof by exhaustion, we're going to check all the numbers between 2 and 6 inclusively and see if any of them divide 7 here. So we're just going to exhaustively try out all the combinations here. So case 2, so 7 divided by 2 has a remainder. Try 3. 3 has a remainder. 4 has a remainder. 5 has a remainder. 6 has a remainder. So and so. And so we end up saying that none of the values between 2 and 6 divide 7 evenly. Therefore, the only divisors are 7 and 1, and therefore 7 is prime. So that's kind of proof by exhaustion. I mean, it's interesting. I don't know if you try this in different AIs. So again, when we're talking about different ways of doing this. So if I have you write a program to find out if a number is prime, are you going to try, like, let's say 1,000 is 1,000 a prime number, or 1,001 is 1,001 prime? Are you going to try out all the numbers between 1 and 1,000? Or are there, because like 2, like when we did 12, we had 2 and 6, or 3 and 4. But so once you find 1, the lower one, you also find the higher one, 4. So you don't always have to try, right, all of them, right? You can go up to, if you're going to 1,000, can you stop at halfway, go to 1 to 500? Because once you get to 500, you don't have to worry. If you haven't found one before 500, you're not going to find one after 500 because you would have found the lower half there. Is that halfway mark as far as you have to go, or is there another limit there? What is the limit when you're trying to find out prime numbers? So for this. So with 1,000, so you have to go to what? Well, let's do 100. If you're going to do 100, how many numbers do you have to try? Do you have to try up to 50? Which ones do you have to try? What's the square root of 100? 10. And so if you get past 10, that means 10 times 10 is 100. So if you really just have to go up to the square root of that value, because if you go beyond that, you don't need to go beyond that, because if you haven't found a divisor less than the square root of that number, then you won't find them because every divisor always have one below the square root and one above the square root there. So ways that are exciting. And AI. So if you put this into most AIs, let's see if well, yeah, we'll try this chat GPT. A lot of them will make that argument and will say, oh, we only have to try out the numbers. Oh, see, this is trying out the numbers 1 through 6 too. That's good. See, that's what I wanted to do here. But let's try one of these models. Because maybe now it won't happen, because this morning I was having trouble. They were all, giving me this sort of stuff. And I had to explicitly tell it to try all the numbers and not stop at the square root of 7, which is only like what, 2 point, you only have to try out 2 then. So, oh, this is doing all of them too. That's good. Well, okay. So again, there are different proofs out there for this, and different ways of doing exhaustion. Sometimes we have to do all of them, and sometimes we really don't have to do all of them. We can make an argument where you don't have to necessarily do every single one, but every possible, you can argue what are the possible values here. So sometimes if we have an infinite enough group of them, you can't do a proof by exhaustion. So then you're doing a proof by induction often here. So let's say we want, 2 to the nth is always greater than n for any natural number n greater than 1. So 2 to the cubed is greater than 3. So what is 2 cubed, right? 2 times 2 times 2 is 8, and 8 is greater than 3. That's what we're trying to say there. And 2 times 2 times 2 times 2 to the fourth is 16, and that's greater than 4. So how do we prove that here? So again, we're going to do a proof by induction. We're going to do the base case when n equals 1 here, because again, we said for any natural numbers n greater than or equal to 1. So we're going to start with the lowest value 1. So we're just going to say if n equals 1, 2 to the first is greater than 1 here. So if we have n equals 1 here, that's what we get up to. So we are just substituting 1 into our proposition here, our value, our equation. And we evaluate 2 raised to the first power is just 2. So 2 is greater than 1. That's true. So the base case holds. Now we're going to do induction. We're going to have a hypothesis. We're going to assume that some value k, this is true. So 2 to the k is greater than k, or some k greater than 1. Okay, so we're going to assume that's true, and then we're going to prove that it's, if that is true, it is true for the next largest one. So for k plus 1 here. So the idea is, let's say we know it for 2 to the fourth. 2 to the fourth is greater than 4. If we know that's true, then can we show it for 2 to the fifth based on the fact that we know it for 2 to the fourth here? We're just relying on the fact we know it. So again, we're going to plug in k, our n is going to be k plus 1 here. So 2 to the k plus 1 is greater than k plus 1 is what we're going to do. So now we're going to try to do this, calculate this. So 2 to the k plus 1 is 2 times 2 to the k here. We already know that 2 to the k is greater than k, because that was our hypothesis. Our hypothesis was that 2 to the k is greater than k. So if we can convert this to something with that value here, we see that. So we'll see that that value holds. So then we have, so then once we know that 2 to the k is greater than k, so now we can multiply both sides by 2 if we do the same equal thing to both sides of an inequality. It still holds for a positive value here. So we can say 2 times 2 to the k is greater than 2 times k here. And now we can combine the last steps we have. So we can factor out the 2 to the k here. And so we can prove that 2 to the power of k minus 1 is greater than 2 to the k. And we can work through this. So, and again, we know that k plus 1 is greater than k here. So that means that 2 to the k is greater than or equal to k plus 1 for this value. So it works down to these inequalities. Again, they're saying here we have 2 to the k plus 1 is greater than 2 to the k. 2 to the k is greater than k plus 1 here. So we can combine those and say 2 to the k plus 1 is greater than k plus 1 here. And that's our base, our case, that we've proven that this is true, that we're testing this out. We want to prove that that's true. And we start with kind of the hypothesis case and build it from there. So this is kind of our proof by induction. We do some base case and we show that if it's true for some value like k, or assume it's true for some value in k and show that it's true for k plus 1. And the argument then is that, okay, it's true for n equals 1. And because of this second one, we know it's true for n equals 2, because if it's true for n equals 1, it's true for n equals 1 more. So n equals 2. And if it's true for n equals 2, it's true for n equals 3, 4, 5. So once you have the base case and then this hypothesis case, you can show it's true for any value here. So that's our proof by induction. And again, it's a good way to prove when we have an infinite number of values. You can't just do a proof by exhaustion because we have infinite numbers of values here. Proof by contradiction is, again, we assume the opposite here. So let's just say, show that there's no largest even integer here. So let's prove that there's no largest even integer with contradiction. So we're going to assume the opposite. So assume that there is a largest even integer, and we're going to call it n. So n is the largest even integer, we're going to say, for this. But if n is the largest integer, we can write it as, so for an integer x is even if we write, so how do we show that integer is even here? It is just 2 times some k value, some other integer there. So if n is an even integer there, we can assume that we can consider the integer m equals n plus 2 there. So we can take whatever our largest even integer is and add 2 to it. And we get a new integer m. But then the question is m even? And is it bigger than n? So it is bigger than n because we're adding 2 to it. And now is it even here? So now we're going to show that it's even here. So we're going to say, here's our m equals n times plus 2, where again, we know that n is an even integer, so we can write it as 2 times k for this. And again, now we can pull out this 2 out of this equation, and we can write this as 2 times k plus 1 here. So now m is 2 times k plus 1. And so that means m is even, because an even number is any number that is 2 times an integer, and this is still an integer. So since k is an integer, k plus 1 is also an integer. So we've written m as 2 times an integer. So m is definitely an integer. So now as our contradiction here, we have constructed integer m. So we know m is an integer, but it's 2 plus m. So we know that m is greater than n. We know that m is an integer, and we know it is even here. So we can we've contradicted there. We said that n was the largest integer, but we found m to be another integer that's larger and still even. So then we found a contradiction here. So our largest there's the largest integer n, even integer n, led to a direct contradiction here, and therefore that assumption is false. So there is not a largest even integer. For any large integer, you can always find a larger one. So again, that's our typical proof by contradiction. I'm not going to go through this whole proof by reduction necessarily, but I'll just talk about it a little bit. Again, with proof by reduction, we're going to take some problem, often maybe a harder problem, and reduce it to a simpler problem we already know the solution for. So let's say that we're going to look at this, the fact that 2 times n is not prime for every prime number n. So if n is a prime number, 2 to the n is not prime. That's what we're saying. So how do we do that? We can't, you say, well, can we just do proof by induction here? So we can't necessarily do proof by induction because, again, n is a prime number. So what is the next? We can't just add one number to it, or you can't say this. What is the equation for the next prime number? There isn't a good equation for the next prime number. So we can't use a proof by induction here. So we're going to reduce this problem to another problem that we have an answer to. So we're going to say that 2 to the n is not prime for every integer, not just every prime number, but any number n greater than 1. So again, proof by reduction for every prime number. This is our and we're going to show this is our original statement, and we're going to show it's equivalent to this statement. For every integer n, the number 2n is not prime. So we're going to do this reduction argument and show that's case. Now, you might have to also, I mean, if you don't know already this is true, you might have to show this is true there, or it just might be something that you can prove or has been proven before. So we're just going to reduce this statement to this statement here, and we're going to walk you through this. So again, and this kind of explains why standard induction fails. So, and why we have to do this. Okay, now we get to my favorite type of proof, and this is proof by diagonalization. I always think these kind of play with your brain in a fun way. I always love, again, the first time I ran into these was with different levels of infinity Cantor sets here. And so I'm going to show you that one here. I don't know if it's a good example, but proof by diagonalization, they're always kind of complicated proofs here. So how are we going to do a proof by diagonalization? So let's talk about, again, what we need is some infinite lists. So we're going to start with integers and what is countable there. And we're going to prove that the set of real numbers between 0 and 1 is uncountable or not equivalent to the integers. That there are more numbers real numbers between 0 and 1 than there are integers values kind of. So again, the idea of countable sets, we have to define that. So countable sets, we have a one-to-one correspondence with the natural numbers, 1, 2, 3. So basically we can count them there. So we can count the integers, even though they go positive or negative. We can talk about a way of setting up to count each one. We can even count the rational numbers, the fractional numbers. There's a way to line those up so that you can count every rational number and set that up here. But let's look at real numbers between 0 and 1. We're going to try to show this is uncountable here. And again, this is Cantor's diagonalization argument. So we're going to do kind of a proof by diagonalization, almost always a proof by contradiction. So we're going to assume the opposite. Assume for the sake of contradiction that S is countable, that the set of real numbers between 0 and 1 is countable. So what does that mean? That means we can count every one. If S is countable, we can list them all out as values here. And now let's remind ourselves how we represent real numbers. We can represent every real number as a list of as a decimal value. I mean, yeah. So 0.4999, stuff like that. There. So there's some details here between there are some ways where we can represent a number that's equal to another representation, and there are ways of getting around it. We're going to skip those sorts of little details here. So now we're going to try to construct a number that is not in our list of rational or values here. So we're gonna say we're gonna have a list. Again, if this is countable, we can list all of our numbers out this way. The first number is 0.D1, D11, again, because this is our first number, D12, D13, D14. So this is all our decimals. So again, 0.4999. And this would be the 4999. Now we're going to list out our second number. Here's R2. And 0 point, and again, we're just going to use the syntax D21, D22, 23, 24. It's like we're doing exercises. And then the next number is 31, 32, 33, 34. Then we do 41, 42, 43, 44, and they all go on infinite here. So we have all of our numbers here. And this is supposed to list off all the numbers in our set. But we're going to show that we can make up a number that's not in our list. So we have an infinite list of values. It's supposed to cover all the numbers, but now we're going to make a new number through diagonalization here. So we're going to make this new number called x here. And we're going to have each of the digits of x, x1, x2, x3, x4. And so we're going to make sure that it's not equal to any of these numbers. So we're going to make sure that x1 does not equal d11. And that x2 does not equal the second digit in the second number, d22 here. And that the x3 does not equal the third number, the third digit of the third number. And so on. And again, you can write this for any, if the second digit of the second if number is 2, we're going to let x be 3. And if it's not 2, we're going to let it be 2 there. So this is how we're going to choose this different number. And so we can construct this, and we can show that x is not equal to R1 because the first digits don't match. And x is not equal to R2, our second number in our list, because the second digits don't match. And x is not equal to R3 because the third digits, and so on, that for every item in our list, we can show that it's not equal to that value. And so we have a number, we have a list of all of our numbers, supposedly. We said it was countable, we could create a list there, and now we can make an item that's in our set that's not one of these numbers. So that's our contradiction there. So now that says that our original supposition was false. We assumed that was countable. That led to a contradiction, so it has to be uncountable. So you're wondering, Tom, why are we doing math? Why don't we do some computer stuff? So let's try to do some computer proofs now that we've seen some of these math proofs here. The simplest proofs are proofs about specific Turing machines and Turing machine languages and that sort of stuff. So again, let's remind ourselves what a Turing machine is here. So we have a set of states, a finite number of states that the machine can be into. We have an input alphabet, and again, this is often relatively simple. So again, we often use this square to denote a blank here, sometimes B. So yeah, and it's generally considered not part of the input alphabet. So we have some blank value that's not part of the input alphabet. We have the tape alphabet here. And again, this includes the input alphabet generally and the blank tape symbol and any other extra values we not need for this. So, and we have our transition functions here. These are usually used, like we usually use delta or some value like that. They're showing, again, this is formal. They're showing it goes from, we're given a state and what is on the tape. So given a state and what's on the tape, we're going to say what's the new state, what's the new value of the tape, and then are we moving the head left or right here. So again, we're given the next symbol, the symbol, yeah, here in a direction. We label at least one, or we label just one state, the start state. So we have a set of states here. One is labeled the start state here. And then we have some states labeled the accept states and some states labeled reject states. And we stop once we get to those states. So now I'm going to prove some stuff. I'm going to start proving relatively simple stuff. So we're going to say, can we construct a Turing machine that accepts strings like with an even number of A's and nothing else? A, so 4 A's, 2 A's, but not odd number of A's, so not just A or 3 A's. So again, we only want 2 A's. So the way we write this often is A to the 2n. So like A to the n would be n A's here. And so 2 would just make it even for this. So that's what we're kind of writing this, is A to the 2n. One thing I see with working with AIs and stuff is that some of them don't work very well with don't recognize subscripts that well. And so you often will see them written this way, A to the power of 2n for this. So just be aware that when you're working with these stuff and superscripts and subscripts, that sometimes that AIs have trouble with those here. So here we're going to make sure we understand our goal, our language. And again, so this is a proof where general systems have trouble with this. So if we just go to like ChatGPT-4 and ask it to do something like this, it tends to have it'll try to do this, but it'll often generate language inconsistencies with this stuff. So again, that's why for the assignment this week, we're going to have you look at proofs like this and compare the standard AI systems and the proofs they generate with some of the deep thinking AIs and how they work here. So again, let's just look and see if we can see any mistakes in this one. So here's our Turing machine here. So again, basically what we have to do is create a Turing machine that recognizes this and then prove that it works here. So here's our Turing machine. We're going to have a start state and another state here. Our tape alphabet is all A's, and then we have a blank symbol here to represent the end of the tape. And here's our transition rules. If we're in state 0, we go to state 1 for reading, and we're reading an A, and we're writing an A, and we go to the right. So we moved that, and now we're in state 1. If we're in state 1 and we read an A, we go back to state 0. We're going to write out an X and go to the right. So it's going to read an A, go into state 1, read the next one, and mark it with an X, and then go back to state 0, read an A, and go back. So it'll go read between these two states, 0 and 1, back and forth as it's reading A's in. Now, eventually, it's going to get the end of the list and be in one of these states and read an empty value here. So if we're in state 0 and read an empty one when we accept it there, because then we've got to end the list and we've read an even number of values. If we're in state 1 and we get an empty one, we go into the reject state here because we read an odd number of values and do this. So again, that describes how the Turing machine works here. And conclusion, it really doesn't prove, it creates a Turing machine, but really doesn't prove, it creates a good thing, but we're asking for a proof. So let's look at how a better AI does this. So again, here's our goal strategy. We're going to check if the input string only contains A's. Then we're going to check if the number of A's is even here and ensure that it halts here. So we're going to construct our Turing machine. Again, this is what we did before. So again, similar stuff. Here we have our blank, our A and X and our blank. Sometimes AI will put in this S cup. It's supposed to just be a blank here. So sometimes it's want to put a box there, but it doesn't. So I'll just tell you that sometimes it's that. And again, we'll see this blank symbol, and sometimes when you're copying and pasting, it doesn't put in the right symbol for that. So here's our algorithm, and we can look at the different cases here. I'm going to put these cases on different lines. Here, actually, I'm just going to do here. So we're going to be reading, we're going to start at our Q state, and then we're going to read our values. And again, this is just kind of arguing or constructing our Turing machine. So we're going to scan the tape from left to right, looking for the first occurrence of an A. Case 1, we found an A, so we're going to overwrite it with an X and change the state to like scan second state and move the tape to the right. Again, if we find a blank here, then we've been reading A's, and then we can figure out which one we are. If we find an X, when we move to the right and continue scanning, and then we find any other symbol, there shouldn't be any other symbols here. So it works through this proof and walks through some examples. So if the input is AA, now here they're they're marking every A here. So we're going to read the first A in and mark it with an X and move to the right. And then we're going to, we're in the second state. And again, we're going to read the second A and mark it with an X. And now we're going to read a space here and move it to the right. Now this actually looks like it has an error here. So again, this is where I think you'll be seeing issues with this. So it is reading the first A and writing an X there and moving to the right here. And now we find the second A and mark it with an X. So we have an X. And then they rewind to the start. So what they did is they first are going through and making sure there's only A's in the tape here. And then they're doing that. So now then they're going to rewind to the start and now see if there's so they're going to take every A, mark it, change it to an X, make sure there's only A's there. Now they're going to see if we have an even number of X's. So we're going to scan the right. We find an X, we move to the right. Scan, we find an X, move to the right. Find a blank, and we go to a final check where it's halt or not here. Again, so they should have these two states here where we're first we find a second A in a pair and we continue scanning there and then we move back for that. And so this is when we've found our first our like odd number A's, and here's for our second or of our pair. So again, if they find it, they're overwriting with X, and we're changing that to a rewind, move the tape until we reach the beginning of the tape. Okay, so again, every time they find an A, they change it to an X and move that to another state, and then they find the next A and mark it with X. So every pair of A's will be marked with X's here or blank here until we get down to the blank for this. And then they're going to look through, and then they should just, the whole tape should just be X's. And if they find any A's left, that means we have an odd number of A's for this. So again, that's what they're looking at. They take an A, make it an X. They're in the second state, make that an X. And then they see a space, they move back. And now they're going to scan and see if they find any A's. If they find any A's, then they know there's an error. Or, there's wrong with this. So, and then so they go through this example with 3 A's. The first A, they put an X. The second A, they put an X. And then the third A here. And then they move back to the right. And so then they never find a pair with that. So. Oh, no, I don't. One of the things that AI comes up with these examples, and I think this is a simpler set of rules than we're doing here in this proof. So both of them are trying to construct a Turing machine and then show that it works here. And I think this strategy is just more complicated. It's writing A's and X's, scanning the tape left to right, where this one simply looks through the tape, reads each A, skips over the first A and the second A, marks it with an X, and it just has 2 states and it goes back and forth with these 2 states. I think that's a little more simpler than this sort of example here. And then again, once we have our Turing machine, we then ask, is it a decider? So we have to see, is it correctly identifying? Is there logic that covers all cases? We look at all cases here and make sure that every case, every possible, it's kind of like unit testing where we're trying out all the possible strings and making an argument that for every type of string that it is either rejecting it like it should or testing or accepting it like it should. So we pass things like a string with a non-A symbol or a string with an odd number of A's or the empty string. All those should be rejected. And then we pass in strings of an even number of A's and it should be accepted. So again, it's kind of like unit testing where we want to make an argument here. And again, this is what it's kind of showing with these walkthrough examples that is happening. And then we do halting. We want to make sure that this halts in all situations. So we look at every possible combination and see that it always halts here. So here they're arguing that we're always converting A's to X's, and the string has a finite length, so there'll be a finite number of A's. The number of A's is always decreasing with each pass. Therefore, the Turing machine can't loop forever. Here, you'll eventually reject or accept this. So you have some argument for why you will not get an infinite loop here. And again, we can look at this sort of stuff for any language. So here's a proof for, we looked at this Turing machine, I think last week, A to the n, B to the n, the same number of A's followed by the same number of B's. That's our language. So it could be like here, A followed by B, or A followed by B. But things like, you know, ABC, B, those are not in our language. BA is not in the language. It always has to start with A and have the same number of A's and B's for this. And again, we're going to construct our language, our Turing machine here. And again, if you remember, the general idea here is that our input alphabet are just A's and B's, but on the tape, we're going to write X's and Y's. So every time we find an A, we're going to swap it with an X and then scan to the right until we find a B and mark that with a Y. Then scan back and find an A and mark it with an X and scan back and find a B and mark it with a Y. So we're going to slowly mark each of these A's and B's with X's and Y's. And then hopefully we won't end up with any extra for this. So again, we're going to read our first symbol. If it's a B, then it's not in the language. It always has to start with A so we can reject. If it's an A, we overwrite it with an X and move the head to the right. And now we keep scanning rights over the A's and any Y's that are on the tape here. And if we end up with a blank, it means there was an A without a matching B. But when we find our first B, we overwrite it with a Y. And then we start moving to the left here. And again, we keep going. If a blank is red, again, we're scanning to the right and we're looking for a B. We didn't find one. We reject it because then we found an A without a matching B here. But again, we rewind the head to the beginning. Here, scan left over any Y's, A's, and X's here until we reach the leftmost position and we try again here. And we look for any B's, or we mark every A we find, we mark as a B for this. And again, I still find that this sort of definition is not great for this. I think it gets it basically right, but again, I think in my mind, um, there are easier ways to write this than what this AI will write for this. So we'll look at that on for your assignment this week. So then our question is, does the machine decide L? And so again, we're looking at two things. Halting, does our Turing machine M always halt here? So again, we can look at the main, there's a main loop here. Yeah, we're replacing an A with an X and a B with a Y. We're always replacing those. And since we have a finite length string, input string, there'll be a finite number of A's and B's. So the number of A's and B's will decrease. Eventually, we'll either find a mismatch leading to a rejection, or all the symbols will be processed and we'll accept it. So I think you make a pretty good argument that our machine cannot loop forever for this. And then we argue correctness. Will it accept all strings in L here? And again, then we start looking at kind of, like I say, test cases. Does it accept an empty string? Does it accept strings like A, B, B? And arguments, yes, we put an X there, puts a Y there, puts an X there, puts a Y there, and then it accepts it here. And that'll work for any set of A's and B's. And then it should reject any one case there. And again, it didn't like its original argument, so then it created a revised version of this argument here and looks at a slightly different version of this algorithm. And one of the problems I have with mathematical proofs is that people like myself get lazy relatively quick. And so if you look back at our early proofs with math, we were justifying every little step here. So we were saying things like, 7 is not, 7 divided by 2 is not. So that's basically, therefore 2 is not a divisor of 7. And we're trying 3, and 3 is not. And we're trying 4. And we start, like we have this proof by exhaustion where we're trying every possible case. Or where that doesn't work, we use this proof by induction and show that it's true for every possible case. But now when we get to more complex proofs, we kind of take a bunch of shortcuts, it seems like, here. So like when we're looking at, let's go down to this, A to the N, B to the N. We're just, and we start talking about, completeness or correctness. For any empty string A, it'll work this way. And again, does it work that way? Again, and so really, to do this correctly, we should be having a whole proof by induction of correctness here, saying, okay, show that it accepts the empty case, and then show, given like that you have a set of A's and a set of B's, and you add one more A and one more B, then it works for that there. So our argument should be that we can do a whole proof by induction that it accepts the cases. And then rejects strings are not in L. Well, there are infinitely many cases of strings not in L. How do you prove that here? And so what do you do for that? And again, we tend to fall back onto what I call unit testing, where you're just testing the common values here and showing that they fail. So case where it contains invalid symbols, incorrect orders, stuff like that here. So again, I think you make some good logical arguments, but I think there's more to that than a proof. So to really do a proof of this, you'd have to do a lot more. Like, what are your options as far as proof? Maybe you do a proof by um, contradiction there and saying that it would accept it. And what would that mean? What does that argument mean? And again, you're still gonna have to break it down into cases. So you're gonna have to do some sort of proof by exhaustion here to list out the cases. Luckily, you have a finite alphabet and a finite set of input, so you can list a bunch of possibilities out there and hopefully categorize those in different ways. But again, the idea is that it's like proving correctness of a program. You can make a conceptual argument for what this does, and sometimes that's as good as, that's basically, this is a more formal version of this conceptual version argument. So in general, how do we prove that a given language is acceptable by a Turing machine? We talk about it recognizing it or halting here. So generally our structure is we define the language, we define the Turing machine at some high level. What is it, how is it going to work? Then we describe it in detail with an algorithm and some of our symbols here. And then we prove the correctness of M here. And then we prove that M halts here. So we prove that it will accept all the legal values and reject all the illegal values. And we prove that given any input, it'll always halt for this stuff. So we can do these sorts of proofs for lots of things, lots of languages, lots of Turing machines and stuff like that. But now we're going to get into stuff of what we can't prove here. So now we can also prove that a certain Turing machine doesn't halt. So we can create a Turing machine that doesn't halt and do it. Here, I'm looking at this Turing machine that counts an even number of A's and accepts anything for an even number of A's. And into this, we're going to, if you remember that Turing machine, it just, every time I found the first A, it was in one state. When I found the second A, it got into a second state. And then when it found that A in the second state, it went back to the first state here, and it kept moving to the right. You can easily take that Turing machine and change it and introduce kind of an error so that it gets an infinite loop. So if it finds an A, it moves to the right. It finds another and goes in the second state. And in that second state, if it finds another A, it then moves to the left. And it just goes back and forth, left and right, thinking it's counting A's, but it's not. One time it's moving right, one time it's moving left there. And again, we can look at these states and we can analyze this and show that we're going to, it's not going to halt on input here. So we can provide that input, look at the states here. So we start with our initial AAA and then an empty spot. We can read in the first A, move to the next spot. And then again, we read, we rewind, and then we mark that with X and move back. And again, since we're moving to the left, sometimes we can then move to the right. And again, we can prove that this is going to loop forever. So we can have an error in our function here, and then our Turing machine will loop forever. And we can prove that this is the case, that there's an error in this program and this program loops forever. So we can prove that a specific program doesn't halt. We can prove that certain Turing machines do halt. So then what is the halting problem here? So we're going to talk about the halting problem here. And this talks about any machine here. And can you write a Turing machine that'll look at another Turing machine and tell if it will halt or not? In the same way, the question you could write, can you write a Java program that will read in another Java program and figure out if it will loop forever there? And that's, again, can you make a Turing machine? We'll look at the definition of another Turing machine and say whether that second Turing machine that you're providing as input will halt or not. And this has, again, we talked about some of the philosophical consequences in history, especially from Hilbert trying to prove all of math and set a good mathematical or, very direct mathematical foundation back in the 20s and 30s here. And so this led Turing to make the Turing machine, basically just to do the halting problem here. So here, we'll do the intuitive proof of this. Actually, I'm just going to show the video, I think, first. Well, here, let's just explain what it does, and then we'll watch the video. So we want to prove that there is not the halting problem says that you cannot make a program, a Turing machine, that will look at other Turing machines and determine if they halt or not. So we're going to prove that by contradiction. We're going to assume that there is a Turing machine that can take any other Turing machine, take any Turing machine as input, look at that program and say, oh yes, look, see, yep, this will halt. It's decreasing here, increasing here. This will always halt there, or it won't halt. But it will always say either it will halt or it won't halt, accept or reject it. It will not, your Turing machine will not loop forever trying to figure out if another Turing machine will it. So then once we have that, we're going to make a troublemaker Turing machine based on that Turing machine and see how it does. I think this video does a better job of explaining it than I do. Let's see. You might find that a program freezes and stops responding. When it happens, it's not always obvious what's going on. In some cases, it's just waiting a little bit of time and the program starts responding again. But in other cases, the program may have entered some sort of infinite loop that never ends. So the program will be frozen forever and it needs to be quit. You might wonder, though, why your computer can't just tell the difference for you. That is to say, we might wonder if the computer can tell whether a program will finish what it's doing at some point. Just last week, I was working from students doing some data analysis on a large data set, and they were running one line of code or one section of code, and it was taking like an hour. And I knew it took a long time, and they kept thinking it got stuck, but it wasn't getting stuck. It was just taking a long time. So again, sometimes these things take a long time. Let's set the scene so that we can define what we're asking or deciding. We can define a computer program as some set of instructions. Program can accept inputs so that the program behaves differently depending on what input is provided to the program. Here, for example, is a program called walk that starts by keeping track of a variable steps, which starts out as 0. As long as the step value is equal to the input of the program instructs us to move forward, turn right, and then increase steps by 1. That keeps repeating until steps is equal to the input, at which point the program terminates. If we give this program to a computer and then give it an input like before, then the computer will repeat the process 4 times, moving, turning, increasing its interval steps. And after repeating 4 times, the program terminates. In other words, when the program is done running all of its instructions, it will halt. But if we give the same program a different input, like the number -1, the computer will keep running this program forever. Every time we run, the step counter increases by 1, but the counter will never reach -1. So with this input, the program will never halt. So here's our question. Could we define a new program call that accepts a program and an input and tells us whether that program will halt when run on that input? This is the halting problem, and it's a famous problem in computer science. The answer, it turns out, is that the halting problem can't be solved.
not only is there no program that exists that can solve the halting problem, but we can actually prove that there could never be a program that solves it. So let's prove it. Let's prove that the halting problem can be solved. We'll approach this proof using a common technique known as proof by contradiction. We're going to start by assuming that there is a program to solve the halting problem, and show that if such a program were to exist, it would lead to a contradiction, some situation that logically doesn't make sense and couldn't possibly be true. Let's give it a try. Say we had some program called halt that could solve the halting problem. You could take a program, add an input, perform some computation, and then give us back an answer. Either yes, the program does halt the input, or no, the program does not halt the input. If such a program were to exist, we could then use it inside of other programs. Here, for example, is a program called opposite. It accepts an input program and then uses the halt program to see whether the input program will halt when given the input program itself as an input. The reason we call this larger program opposite is because whatever halt tells us, we're going to do the opposite. If halt says yes, the program will halt, then opposite will do the opposite and never halt, as by looping forever. If halt says no, the program won't halt, then opposite will terminate and halt the running of the program. So if we have a computer run this opposite program, it'll work like this. We give the program some input, the computer will take the input and pass it along to the halt program, checking to see whether that program will halt when given itself as input. Whatever halt says, opposite does the opposite. If halt says the input program halts, then opposite will do the opposite and loop forever, never halt. Importantly, as long as it's possible to write the halt program, it's also possible to write this opposite program, since we're just adding some logic like additional constructs and loops that we know computer programs can use. But now, here's the tricky question. What happens if we use the opposite program itself as the input to the opposite program? Does the program halt? Well, let's consider what might happen. Following the program's instructions, the first thing that happens is that we ask the halt program whether the opposite program will halt when given the opposite program as input. There are two possibilities. Possibility one is that halt says yes, the opposite program will halt when given the opposite program as input. Then our program does the opposite and decides not to halt. But that doesn't make sense, because halt says that the program would halt in this case. Possibility two is that halt says no, the opposite program will not halt when given the opposite program. Then our program does the opposite and decides to halt. Again, this doesn't make sense because halt said our program wouldn't halt in this case. Either way, we've reached a contradiction where whatever halt says will happen can't possibly be consistent with what actually happened. And if assuming the existence of the halt program was all it took for us to arrive at this logical contradiction, then the only explanation is that our original assumption is wrong, and that the halt program logically cannot exist. There can never be a program that can tell us in general whether a program will halt on a given input. So the next time you see a program that appears to be running forever, know that your computer can't be so sure. Maybe it is running forever, or maybe it's still running for a long time and will finish eventually. The computer doesn't have a way to know. There are some problems, many problems in fact, that computers just can't solve and solve.
Okay, so that's kind of the idea with the halting problem here. And again, this is another walkthrough of it. So assume we have, again, by contradiction, we have a perfect analyzer here that will analyze it. We call this the halt checker. Here we feed it any program and it'll say program P will eventually stop with input I, or program P will eventually run forever with input. So again, we provide this program with some input and ask it if it will halt. And again, this always answer, it will either accept or reject. So this perfect analyzer halts and always accepts or rejects, will tell us that it give us an answer here. So now we're going to make a troublemaker program here. So first we're going to use the halt checker to analyze a program. So again, the troublemaker program will take, again, code P as input, or program P as input, and we'll give that to the program checker to see if it's right. And then the halt checker, and the halt checker will reply back that this program will either halt or not here. And then the troublemaker will deliberately do the opposite here. Reminds me of this. There's a couple kids riddles and stuff like this where you have or brain teasers where you have someone that always lies and always does the opposite. And then what do you do with that? So you remember opposite day or always, these ideas where someone always lies there, and then you can have this problem. So again, troublemaker will always do the opposite of what halting set. And then now we can then recursively kind of feed the troublemaker its own, because it is a Turing machine. We can write out Turing machines as inputs. And so we can feed the troublemaker its own code as input and ask. So if you look at your own code, do you halt or not? And that will create a contradiction, because if the troublemaker code does halt, troublemaker won't halt. And if troublemaker doesn't halt, it will halt there because of the checker. So you can generate a relatively easy contradiction here. And again, you can write this more formally with different proofs here for this. So you can also, once you kind of have this, there's something called Rice's theorem that's related to this. Again, saying that any property, any non-trivial property of a Turing machine is undecidable for this. And you can show that making some property of a Turing machine can be converted or I want to use the mathematical term. What was that proof? Reduced. Yes, not converted. Can be reduced to the halting problem here. So you can always reduce any problem to the halting problem for this here. And again, we can work on different ways. And again, we can prove this by contradiction. And again, we do a reduction to the halting problem here. I'm going to show an example of this, the acceptance problem, and how it relates to the halting problem and the Rice theorem as an example. So here, given a machine M that accepts a string W, and an input string W, does M accept W here? And again, we proved that. We showed that you can show that given one machine and one input string, you can show that that machine accepts that input string. But we want a Turing machine that will look at any other Turing machine at any other input string W and say, okay, given M and W, does this machine accept this string? And you can look at any machine. So again, we've got to be looking at a Turing machine that looks at Turing machines for this. And again, we can map this onto the halting machine. So the basic proof is identical to halting proof. Assume that we have a decider, construct a paradoxical machine that runs the decider, and it accepts if the decider rejects, and rejects if the decider accepts here. And this is just one example of what we see in Rice's theorem, that we can't create a Turing machine that looks at other Turing machines and decides if a machine will, if any machine, look at any machine and any input and decide if that machine accepts that input here. people often take these cases and kind of expound on them and say, so there's so much stuff that machines can't, computers can't do and stuff like that. Um, but all of these cases are when we're looking at computers that look at other, or programs that look at other programs and stuff like that. And we can make statements about programs analyzing other programs. But like here, I ask, what does this apply to a specific Turing machine and a specific input? And no, it does not. We can always, this undecidability of this does not mean that for any particular machine and any particular input, we can't determine if M accepts W. We can almost always determine that. Given some program and some input, we can often look at it and see and prove that that is will solve that. But we can't write it in a general case. This talks about the general problem. It's impossible to write a single algorithm that works correctly for all possible Turing machines and all possible inputs. So you can't have a single algorithm that works for that analyzes all machines and all inputs, because if it does, you can feed itself into it and see how it works. So again, some people like to point to these fundamental limits. To me, I mean, all these limits are places where we are doing this kind of recursive look. We're always, in order to do these things, we always have to create a Turing machine that's looking at other Turing machines and stuff like that. And we're feeding it input of itself. So with this. So although there are some, it certainly shows there are some theoretical limits to computation, it doesn't really talk too much about any practical limits of computation here for this. So that's what we'll talk about on Thursday. Some of the more, we'll talk more of the philosophy, what does this imply, and some of the practical consequences of this. Does this mean we can't, create a linter or something that looks through a program and finds errors in a program, and will look through any program and again find problems in any program, any Java program, for example, or something like that. So we'll look at that on Thursday. Okay.